Good afternoon, participants. Welcome you all for the afternoon session of day 4. Today, we are pleased to welcome our chief guest, our resource person, Mr. Kias Hanifa, Chief Technology Officer from Fonicom Limited, Malta. Welcome, sir. It's my pleasure, sir.
Thank you.
Sir, our resource person is a tech-savvy and passionate computer professional. He started his career as a customer support in 1998 and now with over 22 years of experience, and he has no field left. He is extensively experienced in unified communications, security, networking, cloud, big data analytics. His area of expertise includes networking design and implementation, product design and development, strategic technology planning, vendor management, leadership and supervision, project management, enterprise data management, and building Linux tools. His journey from a customer support of chief technology officer is truly remarkable and an inspiration to all of us. We are humbled by your presence, sir. Now, I would like to request a resource person, Mr. Kias Hanifa, to take over the session. This session is all yours, sir.
Thank you, and that was a warm welcome, and that's a very kind words. I'm very happy to join the session again. Okay, so first of all, good afternoon to all the participants, and I would like to thank for giving me the opportunity to present a topic in your refresher program. I'm very pleased, and I would like to also thank everyone in the first half, like to see that like they would have already had a session in the morning, and now they are continuing on the second session. So I believe that they'll be gaining some knowledge through this presentation. I hope so things go well, and hope everyone is safe on the new COVID situation. Okay, let me start. So the as part of the program now, the topic what I chose was the clustering algorithms. So clustering algorithms, you would have seen clustering, the word, a simple meaning. Clustering is grouping. So it all started, let me share the slide. So this is clustering is nothing but grouping. So we are talking about grouping. So imagine in a crowd of people out there, or what from the conversation, what you can derive? Nothing, because you have to separate the groups, because the groups will be speaking about a lot of topics. They will be involved in a lot of discussions, but you will not, as a third person who is, as what you call, seeing someone from the distance, you will not be able to analyze what the group is all about, why they have assembled, what is the reason they have assembled. So this kind of lot of questions you will have when you are handling a group of people or a mob of people. So this what also applies to our computer standards of data standards, where we use clustering as one of the technologies. So here clustering started from the data what we evolve daily, like what you call like supervised data, unsupervised data. So supervised data, like a target. So I'm looking to find some the highest salary or the lowest salary. I am trying to find a good match or something like that. So you already have a label for the data, and those data is easy to even recognize and get a pattern with supervised data. But clustering as a concept is not for supervised data. It is from a unsupervised data, where you are going to fetch some patterns, and this we are facing it daily. Like I mean, like we handle data daily on a day-to-day means, and every second, every minute, but we don't know what value or what insight we can derive from it. So this is one of the biggest challenge for clustering to evolve into a new science in artificial intelligence, where this has become one of the very famous methods of finding deductions and recognition patterns from an unsupervised data. So like as I told you, that daily you have some data, like it could be your emails or your document search. You are handling a lot of documents, and as an online shopping store manager, for example, the customers come in and go out. they have a lot of logs left. So those things, we don't know what to do with this data. So when you start looking into this, you don't know what you're looking for, but you may arrive at some pattern or some recognition patterns which will be helpful business wise and commercial wise. So this is where clustering is one of the biggest advantage, to know something from an unrecognized pattern or unrecognized data. So we are trying to search something from a bulk of data. From the data, we are trying to find what will be valid for us, what will be something very good for our business strategy, what would be good for our for a search algorithm, or what could be, like, it has a lot of insights. We can build a lot of insights from a simple method. So, like, to give a bit of context how this clustering evolved, how data was started, how, all those things, but I'm just want to give a bit of insight so that we will start data as an oil, where we got into multiple segments of supervised and unsupervised data, and then arrive to the clustering algorithm as a final way of conclusion for this particular session. So what I'm going to do is, like, I'm going to give a bit of background how all this started. So today we have really huge amounts of data. So we have in terabytes of data generated every second. So this is could be from mobile devices, from photographs, from web documents, Facebook updates, tweets, blogs, user generated content, IoT, transactions, sensor data, surveillance data, the queries what we do, the clicks what we do, the browsing history. So these are all, like, what I call, these are all unstructured and unlabeled data what we do daily, but we don't know how, because these are all clustered into one segment just as a data from the whole as a raw data which we have. So this is the resource what we have right now. So we have generated a lot of data. It is always generating. We're always generating now and then, and we are keeping generating. So this has to be analyzed to extract the knowledge out of it. So what we did, so even for example, when we started to explore data, it had to be done with complex algorithms and decisive models and all those things, and prediction models and all. So the pioneers were like the big companies like Google has evolved, and they solved a lot of natural NLP processing problems simply by looking at the data. So the example could be when you type on the Google search screen, you do misspellings. You will do a synonym for of a search. So those things and all are corrected and suggested and given a close match from Google, because they use a natural language processing, because of the audit trial, because of the search trial which you have already given, and what others have also searched and what they have already associated for. So this is how Google was able to solve a lot of problems on search when they started to extract the data and explore it properly and harness the collective intelligence, because that is the power. Because daily you use Google, we use Facebook, we use tweets, we use Amazon transactions, we use Flipkart transactions, all those things. These are the assets of the online company now, because they are trying to build a pattern, a data science model, wherein they can harness the data what you left in a more intelligent way and more intuitive way. So this is the whole goal of the data. So the goal of our data is to do something which is intuitive and which is very fast and which will bring some value, business value and strategy to your whole data science as a project. So that is where data was harnessed in a very collective intelligence way. So this is the exploration phase, what you have done with the resources, what we left behind as a data. So that is the start. So the data are always very complex, because you will have different types of data always, like it could be tables, time series, images, graphs, spatial, temporal aspects, and also like the interconnect data types, you know about it. So like when from a mobile phone, we can collect the location of the user, his friendship information, He checks in where he has checked in, his opinions on the Twitter, his tweets, the images what he collect on the cameras, and the queries to the search engine. So like whenever I reach a place, whenever I go travel a place, what I do is I search for the hotels, for the restaurants, for the tourist places. Then this is context wise. I have to, like, you have the algorithm maps suggest you the right place in the right location, because based on your location, because when you are in a place in Pondicherry, then you will be suggested to the places to visit in Pondicherry, not in Chennai or not in Bangalore. So this is more concise and targeted to your to your information what they have collected. So these are more of an interconnected type of data that is we are always seeing, and which we already use it. So we may not know how this is done, but the background has a lot of work to be done. On a transaction wise, on like today, like we go to online shopping, we go to shopping malls, we go to like brick and mortar shops, like we do our purchases. So it could be anything. So as a real life customers, what we do is we do like Walmart. I'm just giving as an example, like any it could be any shopping mall. On AT&T, you can or BSNL or Airtel, or Vodafone, Jio, whatever. You make a lot of calls. You use your credit card companies, do your transactions. You are the POS, and you give information, and also you pay for the what you have like purchased. So you are doing a lot of transaction data at each and every moment and each and every aspect of life. So it could be like your retail shopping or a wholesale shopping or online shopping or brick and mortar shopping, whatever it is. So you are leaving some trail. Of your data, which like is associated. Okay, this person has bought this. This person has bought this. So like this way, transactions data is classified. So every record, like for today I bought like for bread, coke and milk. The next day I would have bought something else, and the third day I would have bought something else. So there is always a change of attitude, change of business pattern, change of purchase pattern. At every moment we see something. So this is the transaction we do so far. So data, we are seeing data into multiple multiple layers of data, where we are seeing now the first is the transaction data. So transaction data is collected at the shopping or the bank transactions what you do. So now this set of items can be represented as a binary vector, where each attribute is an item. So for example, bread, coke, milk is also a vector. So everything is an item there in the vector. So it could be a count of words, it could be a set of words, which that is the transaction data we have seen. That is a set of items. It could be like on day one you have bought this, day two you have bought this, but it's all just like vectors. We are making some vectors, and those vectors, it's just values and counts and words. That's it. So there is no relation. Why you bought it, when you bought it, nothing. Like on day, there is no relation of the time and what you bought. It is just a data that is collected at today. This person at such and such time bought this. That's it. And tomorrow the same person can be tracked, and he would have bought something else, or he might not visit that place for a while, then he come later. So this kind of data is always stored in your online shopping or in your retail shopping or whatever. So this is the start. Where you live, where you start to give data. So that is the first step. Now also on a browsing level, what we do is we go to web. We browse billions of we browse a lot of web pages. We get into Wikipedia. We get into the news portals. There, for example, now if you look into the COVID-19 news item, this is one of the the biggest trending news item always in the last 2 years or 2.5 years. You would have seen there are a lot of companies who did clustering, like, for example, they tried to bring all the news items together and try to find a cluster of those news items. It was stunning to see that there are a lot of keywords which were closely related to COVID-19, and those documents are all related to one and each other, but by one way or other means. So this news item itself, because these are not documents, these are articles which are written about COVID-19. But what happens is there are some keywords there are repetitive keywords, frequent keywords, which will be able to associate a news item in India with a news item in Australia, or a news item in India to a news item in US. So like there was some kind of like what you call information research that has been done and correlated in a way that, okay, these two keywords come from the same origin of vector, that is COVID-19. So this is the way, this is one of the biggest asset we have. So like I would have written an article here, but someone would have written an article, but we might tend to say the same thing. So that is the beauty of it. And Twitters, we always see the Twitters, we can always see a lot of Twitters that is done every minute. And the document, this is, as I told you, for the COVID-19 as an attribute itself, like for example, document 1, document 2, document 3, I'm just taking a snippet. There, like the first document has a keyword team repeated 3 times. The second one as a coach, the third one as a player. But all this, if you see these 3 documents, if you relate together, it is something about a game or a score or a sport. So if you look into data, so the cluster representation, even though you go near and near and start digging into, get into closer way of things, then you find that they are talking about a common goal or a common topic, which is something called sports. It could be divisive. It could be something like you can make it into football or a volleyball or a cricket or whatever. So, but what happens is, from this whole cluster of documents, we are trying to find a corresponding word, a corresponding term that will be common element for all these documents, and that is called the clustering and getting the topic out of it. So we are trying to pull a topic from all these unstructured documents or split irrational documents, and finding a common element and a common term which can relate each other. So this is where we start. So this is where how we start this kind of clustering and getting the common goals together. So that is document data. So I'm just giving a small example. Here. What happened is here. This is just a small graph which I took from Gaggle, and one of the most famous online machine learning and artificial intelligence competition platform. There you see this happiness index scores through the years, and see here, based on some attributes of the population, GDP, the spending score, then everything. What they arrived is the happiest countries in the world. And if you could see that Finland was highest on the score, on the mean score, because it was done with multiple clusters of data and attribute. But what happened is, this was not in over a period of time. This is done on over a period of time, taking a lot of attributes and putting a score and doing something called an index score for the happiness. So what they have done is, for happiness, they would have taken GDP, they would have taken health, they would have taken hospitalization. Everything would have, all the possible factors would have been accounted for. Then the cluster would have been formed with this elements to find the happiness score index. So this is how the data, but this no one would have known that this could be arrived out of all these elements, because we are trying to find something from an unlabeled data. Like for example, it has all they never know what they were doing for, but it was all segmented and got down to a point that the happiness score is something like this. So this is one example how data can be harnessed and put it in a way that this could be presented in a more readable and legible format for a country itself. So this gives them some strength. But the data analyzing was not easy. It was taken from a lot of steps, and it would have gone through the iteration process and all, which I'll explain later. But how the whole point was, the whole data science behind this data. Data gives you this strength to arrive on something which is a better insight. And next one, what I'm showing you is also an example, is between the hospitalization charges based on the age. The first one, if you see, young adult, senior adult, elder, then their charges. What happens is, a senior adult, when he goes for the hospitalization, he spends more compared to an young adult. Then elder spends the next to the category based compared to young adult. So this is the charges, this is between the age and the charges relationship. See, this is again taken from Gaggle as a competition exercise, and we are able to show that as in a simple graph as a cluster, where you are able to see the hospitalization charges comparatively between age and the hospital charges. That is the first thing. Then the second one, where we are doing some relationship conditions with weight condition, age, and charge. We are adding one more criteria, that is, if you have seen, there are on the legend: overweight, obese, normal weight, and underweight. So the person who are of overweight are spending around the mid-range of the eldership. Those who are younger, they are coming down, and those who are normal, or those who are obese, they are going on top. They're going on top. So if you see this relationship between the age factor, the condition factor, the charges tend to go up and down. And there is again, then there is a graph between, like a cluster between two things. One, the smokers and the charges spent on the hospitalization. Again, the smokers spend more on the charges. So this like every category, like we are able to split into a lot of things of lot of data. All those things was possible because of data. If you go on the history of data, in the last few decades, we have collected so much data, and we are able to harness it into a completely intelligent dashboard, wherein we can get to the granularity of each and every sector, or even every type of it. So we have the power, we have the tools, we have the technology to even go into the more of a granular way. So that is the power of algorithms and artificial intelligence. Then I told you about the COVID. I told you about the COVID cluster documents. So this is again, I have taken the document from Kaggle, and I'm just giving. See, if you look into all the documents, which have been published, it was amazing to see and stunning to see that what happens is, the keywords, we have built the clusters based on the keywords. This is, I'm just scratching the surface of the keywords which we see, but there are a lot of keywords which are spread, and they are related to one each other, like pneumonia, asthma, influenza, HMP, detect, bees, airway, pathogen, bacterial, everything. Like if you go through it, like everything is somehow or other related to the COVID-19 literature. So this is the way they organized. So even to organize the data of the COVID literature, clustering was helpful. Clustering was, because you are able to, if you would have already seen these keywords, I think pandemic we have seen, RNA would have seen, asthma we have seen, pneumonia we have seen. So like if you get into this detail of it, like somehow or other, most of the keywords are related to the COVID-19 literature. But this was done again not in a one day or day, but it was collected from all the news items, then put together, then it went through the process of the iterations, clustering and all, like which I'll show you later. So like this, what happened is, you were able to relate, group documents under one heading of COVID-19 as the topic. But again, like this follows into a lot of subdivisions and divisions and all. But again, I'm not going to discuss on those things, but I've just given a sample of the keywords which was picked up from those literature. So you would have seen this is something the way we see data. And our regular social media data you always seen, and like we have seen, like we do like around more than 50 million pages, a billion pages are there. Facebook has 500 million users, and Twitter, everything. Like we always give social media data, we share data, and we always leave data on the social media as well. So, and on the genomic data, like the genomic data is always there, and environmental data, like the temperature stations, the precipitation stations, and pressure stations are right. And the last but not the least is the behavioral data. So behavioral data is the GPS record positions, your camera produces images, communication via phone and SMS, text via Facebook updates. So like this is more of what you call behavioral data. And Google, Index, Bing record all your browsing activity via toolbar plugins. They also record the queries you searched, the pages you saw, and the clicks you did. So the data collected of millions of users is on a daily basis is increasing and increasing and increasing. So with this, can you classify it, or you can categorize it, or can you cluster it manually? It's near to impossible, because you have so much of data, and with all those data, it is something on a manual process, you can't even think about it. So that is where we are looking into automations, into technologies of IT clustering, or into various algorithms of artificial intelligence, and get into a what you call data science as the major topic or major header, where it will cover all the subjects, all these headers. So now we have seen some examples of data. We have seen like behavioral data, we have seen social media data, we have seen enrollment data, we have seen transactional data. All those things we have seen like few slides before. But when you see this, because everything has to be defined, like we are defining it with a name. Now, this data, what is a data? A data is a collection of objects and their attributes. Then what is an attribute? An attribute is a property or characteristics of an object. Examples: eye color of a person, temperature, etc. Attribute is also known as variable, field, characteristics of feature. A collection of attributes describe an object. An object is also known as a record, point, case, sample, entity, or instance. So here, when you see the example, I think everyone is following, I believe. So like if you want, I can stop at any moment. Sorry for that, I didn't ask about that. So you all hear well, no? That's not true. Is there any problem on that? Sorry. It's all good, right? Okay. So I'm taking that as a consideration, like as a green flag. So what is data? Like a data is a collection of objects and their attributes. An attribute is a property or characteristic of an object. Examples: eye color of a person, the temperature, etc. And a collection of attributes is an object. So here on the right side, if you see, there are two different variables for a person: whether he is single, what is his income, whether he has a taxable income, and what is his, whether he was something refunded, not refunded, all those kind of attributes. So, and the collection of attributes becomes an object as well. So this is the first way data. We are trying to see data as a object. Then the attributes. The attributes, now I told you some examples of eye color, temperature, all those things. Now we are trying to classify, segment the attributes as categorical and numerical. Categorical, like it's more of a nominal or ordinal. So no order or comparison of ordinal, but not comparable. So examples you see: eye color, zip codes, words, ranking, good height, all those things becomes categorical. And numerical, always, like for example, you know that dates, temperature, time, length, value, count, etc. And this becomes the two major attributes, because the reason why I'm going into these small things is because we will be able to see the big picture of it while you're doing the clustering algorithm. So that is the reason we are getting into these small details of attributes and all. So attributes, we have numerical and categorical. And a numeric record is, you know about, I did not explain about the numeric record, and also the categorical record you have seen now. And ordered data, if you see this as an ordered data, below is a genomic sequence data, like you see it's a long string, is a long ordered string. With this, because since we are trying to handle all the data, we have to see what we are handling, whether it's a sequence data or an ordered data, or it's a numeric data, or a category, or what kind of data it is, so, or a time series data, or whatever. So like we have to know what kind of data we are going to handle also, because this also decides on what approach you are going to do the cluster. So lot of dependencies and everything has to be done based on this. So we start with the types of data. Then the time series data is there, like time series. Now you see this, the Microsoft stock daily exchange. I'm just going to share a graph. So it is the graph of the Microsoft stocks. This is a time series data. This is how time series data is done. Like on a period of September to February, you see that there is ups and downs. So this is time series. And graph data, like one related to other, like a web graph or a linear dense linear system or something like that. So this becomes a graph data as well. So I am trying to summarize. I'm going to try and summarize data as numeric data, categorical data, set data, ordered sequences, graph data, which are generated from all the means. Which are the means? Transaction data, then social media data, network data, then the temperature, then the all kind of data, all the sources we had. We are trying to document data, for example, everything. We are classifying that into different types of data as numerical, categorical, set data, order sequences, and graph data. So this is how we are trying to harness each and every step, because everything is a step. Because if we don't have a proper understanding of what we are doing, then it will be a bit of a problem. So that is the reason we are getting into each and every step in a more structured way to see that like we are handling the right method. Now, what can, for the first scenario, what can you do with the data? Suppose that you are the owner of a supermarket and you have collected billions of market basket data. What information would you extract from it? How to use it? So you would have seen the transactional data that I was buying first day as bread, coke, milk, second day as something like that, third day, fourth day, fifth day. So like somehow so what I do with this data, that is where the query comes. What I do is what if I have been online store? What if I had been in an online store? What do I do with this data? That is the question mark. So you can do product placement, you can do catalog creations, and you can do recommendations for a customer. So for example, you bought this, you can buy this. You can do a catalog creations, for example, like in this rack. So you can pick the most frequent elements, most frequent items. Then the product placement, like you can show the visibility, you can do some promotions, all those things you can based on the data. You know that, for example, Coke is something selling at this period of time, or bread is selling at this period of time, then you can do some promotions, or you can do some catalog creations which says that, okay, if you buy this, or you get an offer like this. If you can also recommend this, okay, there is a new multigrain food in the bread in the friend or basket, can you try? So this kind of market intelligence can be done with the data I have collected. So I have the market basket data. With the data, I'm doing product placement, catalog creations, and recommendation. So this is my goal, and for that data is used. Then what I do with your search engine data? Suppose you are a search engine and you have a toolbar consisting of pages browsed, queries, pages clicked, ads clicked, each with the user ID and timestamp. What information would you like to get out of the data? You can push ads, you can do query reformulations. So query reformulations you would have seen, like for example, when you are trying to search something, Google will search you whether they will suggest something. So it will reformulate your query, whatever you are searched for. So that is the power. That is the power of the data we have collected, and that is the goal which the search engine are doing now. So, and ad click prediction. So for example, like when I'm trying to search for some tourist hotels or something like that, they can push some ads, some of hotels in that place. They can give some, like for example, some offers they can show some offers of the hotels which are prevalent in that area. So these ad predictions can be done based on the pages browsed, the queries, the pages clicked, ads clicked, etc. So that is the harness, the intelligence you do with your data product. So that's how things are done. Then now I've seen the genome data. So genome, suppose you are a biologist who has microarray expression data, thousands of genes and their expression values, or thousands of different settings. Example tissue. What information would you like to get off it of your data? So like you could have seen this. So now, because this kind of microarray suppression data is also because the pharma industry is booming now, the microbiology industry is booming now, and what you can do, you can group of genes and tissues. Then you are the owner of a social network and you have full access to the social graph, and what kind of information do you get out of your graph? You can see who is the most important node in the graph. What is the shortest path between the two nodes? How many friends two nodes have in common? What does information spread? What does information spread on the network? How does information spread out? So this is how Facebook or LinkedIn or any other, even I think the new Trump's social media, which is going to be Truth of Social. I think everything will be based on this simple formula. That is, who is the most important node in the graph? What is the shortest path between nodes? And how many friends two nodes have in common? Like then, because you would have seen the Facebook suggestions, your video suggestions, and in Facebook, like what you have to watch, who you can, who they are suggesting as friend, which group you can go subscribe to. Everything is based on this node concept, the distance, the social distance. I mean the social graph distance. So this is again the power of data. And if suppose that you are a stockbroker and you observe the fluctuations of multiple stocks over time, what information would you like to get off your data? So this is the Microsoft graph which I've already shared. So there, so if you have seen, like I'm trying to group a lot of stocks over a period of time, then what happens is I'm clustering the stocks, correlating the stocks, and I'm doing the prediction of the stock value. See, this is everything. Like for example, nothing is happening out of the box. Like for example, everything is generated, Microsoft INTC, C daily, BAC daily, everything. You have the daily stock values. You are clustering the fluctuations over a period of time, and based on the algorithms, you are able to predict whether it's up and down or low, or whether it will fall down or fall. So this This intelligence, again, everything we are trying to make it from the data. So if you have seen, like in the past half an hour or 45 minutes, like we have discussed enough the sources of data, the types of data, and from where we get data, and how we can utilize data as an applicable, what is the application of it, what is the goal of it, and how can use it in a more theoretical way, in a hypothetical way. We have seen hypothetically we can see that we can able to harness data, but how are you going to do this? How, what is the way, what is the method you are going to do it? This is going to be the next question, because otherwise we can always talk like I can do this, I can predict this and all, but what I'm going to do this, how I'm going to do this? See, confining to the topic of this afternoon, I'm trying to like just focus on what you really need. So what I've given so far is the background of the data, the context of how data is generated, how that is getting incremented day by day or minute by minute from all the major sources. That is one topic, because that is data engineering on its itself, or the part of the data science. That is one segment of itself. But now, without that basic concept, I can't jump into the clustering algorithm. That is the reason I wanted to get into the exploration later, but first give some background. So now here, clustering is like part of the unsupervised learning. So we have supervised learning, that is different, because there we have the classifications and all, like it is different. But here, just clustering of this is why clustering is used, because we are targeting of the unlabeled data wherein we don't know what we are going to search for or anything like that. So that is where we are taking clustering as a major mode, and that which falls under the unsupervised learning. So clustering is a data mining technique for grouping unlabeled data based on the similarities or differences. See, it doesn't mean that, okay, it has to be the same, it could be the differences. So that is the straight definition of it. The association is another type of unsupervised learning method that uses different rules to find relationships between variables in a given data set. This is association. Third one is dimensionality reduction, is a learning technique used when the number of features or dimensions in a given data set is too high. So I'm just going to focus on the clustering part of it, but it is coming under unsupervised learning. So clustering is a major topic for us now. For clustering, while you're trying to do the harnessing of the data, you trying to use all these artificial algorithms, intelligent algorithms, either supervised. Hello? You need something? Sorry. So either it's supervised or unsupervised or whatever. So here, if we go through it, how this is done, okay. Coverage, clustering is like, that is what you're going to get in detail now. Classification, ranking, exploratory analysis, frequent item sets and association rules extraction. So these are either belong to a supervised model or unsupervised learning techniques. And this, let us go into clustering as a model now, as a learning way. I've already given you the clustering definition earlier, and now again going to what is in detail. Given a set of data points, each having a set of attributes. So now I already told you what is an attribute and a similarity measure among them. Find clusters such that data points in one cluster are more similar to one another. Data points in one separate cluster are less similar to one another. So how the similarity measured is, it is done with the Euclidean distance if attributes are continuous. Okay. So again I'm saying that clustering, you have a set of data points. each having a set of attributes. Now you know what is data. Like for example, you have whether it's a stock data or it is a document data or a network data or a social data, whatever. But having its attributes, what kind of the attributes for a stock data, it could be the prices or or the date and time or whether it's up and down. So like those are the attributes and the similarity measure among them. For example, when I'm comparing, for example, Microsoft data with the Google data or stock data or Microsoft with the Netflix data or Amazon data. So like these are all stock market data which you're trying to analyze with the based on the attributes. The common attribute is their price or the stock price or something like that, whether it's up and down or something. So we are trying to what you are trying to do is a similarity measure among them, find clusters such that data points in one cluster are more similar to one another, or and data points in separate clusters are less similar to one another. So this is our goal. This is our goal of cluster definition, because now we are trying to see whether this is an unlabeled data and an unsupervised form. So now when you are trying to group it, what happens is, in general, a grouping of objects of such that objects in a group are similar or related to one another and different from or unrelated to the objects in other groups. So again, like there are multiple definitions of clustering, and I'm trying to, the first one is the straightforward one, the second one I'm giving this way. So now you know whether it's an intercluster or intra-cluster. When you form a cluster, among the data points, there is a distance that is formed within the intra-cluster or inter-cluster. So this again, I'm just as a present illustration, I'm just explaining, but we'll go in like in few steps again. So now, in general, a grouping of objects such that the objects in a group or cluster similar or related to one another and different from or unrelated to the objects of the other groups. Now, the clustering techniques. What are the different types of clustering techniques used? Partition methods, hierarchical methods, density-based methods, graph-based methods, model-based methods. Under partitioning methods, you mean the famous K-means algorithm, K-medoids, K-modes, fuzzy C algorithms. Under that, if you see Pam, Clara, Clarence. Hierarchical methods, you have divisive and agglomerative methods. Under divisive, you have Diana. Under agglomerative, we have Agnes, Birch, Cure, Rock, Chameleon. Under density, you have DB-scan, which is one of the famous ones, and Sting, Click, Dentlu, Optics, Wave Cluster. Then graph-based method, you have MST clustering, Opossum, SNN, similarity clustering. Then model-based clustering, you have the EM algorithm, AutoClass, Cobweb, and ANN clustering. So I'm going through the clustering techniques again. So the clustering methods we are trying to devise into 5 methods: partition methods, hierarchical methods, density-based methods, graph-based methods, and model-based methods. The partition-based method and hierarchical-based method and density-based method is something which is often used. And under partition method, if you see K-means algorithm, and in hierarchical methods, divisive and agglomerative, and density-based DB-scan, density-based scan. So these are some of the most common methods of clustering techniques used. So this is the overall. I might have missed something, but from my knowledge, from the information, this is what I was able to concise it. So let us take into the clustering algorithms, K-means, hierarchical clustering, and DB-scan as something we can skim through now to have a insight of what's happening on this, because we'll not have time for covering everything, but I've just chosen K-means, hierarchical clustering, and DB-scan. So to brief again from the beginning, so what we did is we have the situation of clustering. Why we have to cluster? Because of the unsupervised data. From the unsupervised, what is unsupervised data is because there doesn't have labels or anything like that, or no classification. For that, we have to see how data is generated, where the data, what are the sources of data we are looking into, and how data is like classified, like what are the different types of data is there: numerical data, categorical data, graph data, etc. So we went into all those things. Now we are focusing based on the clustering techniques. So sorry, on the unsupervised learning and the supervised learning. And supervised learning is out of the scope for this now. Under unsupervised learning, we are taking clustering as the method. Under clustering algorithms, we are seeing multiple techniques, like on the 5 different methods. Now on the cluster, and again out of those we have chose k-means algorithm and hierarchical clustering and db scan as something which we can go into a bit of in detail to see how it's happening. So again, it is the same. Okay. Now, in this clustering application, my goal is to find groups of documents that are similar to each other based on the important terms appearing in them. Approach: to identify frequently occurring terms in each document. Form a similarity measure based on the frequencies of different terms. Use it to cluster. Gain: information retrieval can utilize the cluster to relate a new document or search term to clustered documents. So I have shown you the example of document clustering earlier. Like, we were able to see the COVID-19 literature, where it was the news items, like different news items were taken, and the common terms on the similar terms were all fetched, and a cluster is formed for that. So here again, my goal is to find the groups of documents that are similar to each other on the important terms appearing in them. So in our, like, for example, in the example what we have seen earlier was the COVID-19. So the COVID-19, the important terms, even though it's COVID-19, but we have seen pneumonia, asthma, pandemic, viral. Like, there are a lot of keywords which are repeated, and those keywords is the common terms which you will be again seeing and seeing. So in order to, what is the approach we are going to do? That is, we are going to identify frequently occurring terms in each document, form a similarity measure based on the frequencies of different terms, use it to cluster. So what is the gain out of this is, we can retrieve data of those important documents and search term to cluster and for example, like pneumonia is a word. For example, if pneumonia is a word, we know that pneumonia, which is under the context of COVID-19, is repeated in these documents these times. So what will be the closest match for pneumonia document? So it will be document 1 and 4. So for example, pandemic, what is the closest document? So we are able to do information retrieval. That is the game. So our goal was different. Like, the goal was to just cluster the important documents. And what we're trying to do is, we find a similarity measure based on the frequencies of different and use it as a cluster. So this is what we are doing, and we are gaining as what is the side thing we are getting, what is the important benefit you are arriving is, we are doing an information retrieval. So as simple as that. So the information
Sir,
hello
what is mean by clustering application to?
hello
Sir,
yes.
what is mean by clustering application to?
No, that was an example. This example is for the hierarchy. So that is the example. This is an application to, I'm just taking this for the example of k-means. I'm taking this because this one is for hierarchical and this is for
Document
k-means.
clustering.
So I'm taking k-means now. Okay. The slide is, application is just what I'm saying is an example. This is an example. Okay.
Thank you, sir.
Thank you. So clustering of S&P 500 stock data. So this is also again, I'm actually a good point that uh, uh, the applicability. What I'm trying to do is I'm taking example for each and every scenario of k-means, hierarchical clustering, then for DB scan. So in this, like for example, the clustering of the 500 stock data also. This is also an example. So what I'm trying to do is observe stock movements every day, cluster stocks if they change similarly over time. So this is the what I'm saying. This is examples of clustering. These are the challenges we have. Now we are trying to derive out of it. So what is the basic idea? So you have the data points. You are grouping together similar instances in the 2D. This is a 2D point patterns. So these are clustering. We are like grouping into similar points, similar instances. What could similar mean? Similar means small equivalent distance squared. The formula is there. Clustering results are crucially depend on the measure of similarity or distance between points to be clustered. So I'm trying to cluster groups which are similar based on the Euclidean distance. And clustering results are crucially dependent on the measure of the similarity or distance, because I can't cluster dissimilar items. I have to only cluster similar items. So that is my goal is first. On that, what I'm trying to do is whether I'm going to do a hierarchical or a partial set of clusters. So I want to cluster a set of, my goal is first of all, I'm going to partition the clusters, because cluster is the important method of doing the the learning experience. For that I need clusters. So for that cluster, a clustering is a set of clusters. Important distinction between hierarchical and partition set of clusters. Partition clustering, partition into non-overlapping subsets such that each data is in exactly one subset. Hierarchical clustering, a set of nested clusters organized as a hierarchical tree. So what I'm going to, partition clustering is k-means algorithm. Hierarchical clustering, I am going to use algorithmic or divisive. So when I'm trying to choose the cluster, what is the approach I'm going to do? Whether I'm going to do a partial clustering or a hierarchical clustering. So this is something what I have to decide. So for that only, I'm trying to first of all let you what is there. So partial clustering. Here you have this original, these are the data points. Now you have done the clustering. So you have done 3 clusters. 1, 2, and 3. You are your original points here. Then you are split. We have done the clustering and made into 3 partitions. If it is a hierarchical cluster, you make a traditional dendrogram. P1, P2, P3, P4. So what happens is P2 and P3, they are closer. So you first form one cluster out of it. Then P4 is closer to the cluster of P2 and P3. So you make a cluster out of it. So that P2, P3, then it is clustered to P4. Then this cluster of P2, P3, and P4, it becomes closer to P1 and you make a cluster out of this. So what happens is you form a tree with the data points you had with the P1, P2, P3, P4 in a more traditional way. You can also do like in a non-traditional way, like what happens is P1, P2 becomes one cluster and P2 and P3, P4 becomes one cluster. So this is the way you see as an hierarchical clustering is done. So you are trying to see which is closer, P2 and P3, then you start. Then you start a cluster out of it, then P4 is closer, you start a cluster of, add the cluster. Then you join the cluster of P1. So this was a hierarchical clustering. Like respect to partial clustering, what happens is you try to similar items, you are trying to just group it and make into 3 partitions or 3 clusters. Now these clusters, we can have different types of clusters. well-separated clusters, center-based clusters, contiguous clusters, density-based clusters, property or conceptual clusters, and objective-based clusters. So I'm repeating, the major problem of clusters is outliers and convergence. See, you have to form a cluster. Forming a cluster is the most important task of a clustering algorithm. Without that, you will fail in your whole exercise. So that convergence, which is the most important thing, what you are going to do, whether you are trying to form a well-clustered cluster, well-separated cluster, or a center-based cluster, or a contiguous cluster, or a density-based cluster, or a conceptual cluster, or an objective function-based cluster. So this is the most important criteria even to start grouping or clustering it, because without that you will not be able to start the process. If you see in detail, if you see in a more of a visualized way, well-separated cluster, you have three well-separated cluster. A cluster is a set of points such that any point in a cluster is closer or similar to every other point in the cluster than to any other point not in the cluster. So what happens is the blue cluster points, so blue, red, and green. You have three clusters. If you see, they are similar items placed on each and every cluster. They are not different. They are not different to each other. So each and every cluster has their own set of items. That is where the well-separated cluster is formed. So the first one, what we have seen is the well-separated. The second one is centered cluster, center-based. You see this, a cluster is a set of objects. The definition is the same. The center of a cluster is often a centroid. The average of all the points in the cluster is the cluster or a medoid, and the most representative point of the cluster. A cluster is a set of objects such that an object in a cluster is closer, more similar to the center of the cluster than to the center of any other cluster. See, if you see, there are two, the red and the blue, two clusters are formed, but what happens is something is close to the center of it, plus something like the distance is not much. So the centroid is formed on the center of the cluster, which you see that the center-based cluster is more similar. Contiguity based, the contiguous cluster, nearest neighbor or transitive. A cluster is a set of points that such that a point in a cluster is closer or similar to the same definition again. But you see here, there are 8 different clusters. There are 8 different clusters, but they are continuous. They are continuous. Somehow they are continuous. So this is a contiguous cluster. Then comes the density-based cluster. So a cluster is a dense region of points which is separated by low density regions from other regions of high density, used when the clusters are irregular or intertwined, and when noise and outliers are present. You see here, there are a couple of outliers in the first one. That's why the density-based cluster is something like a curve which is going out of the outlier, but it still can't be in that cluster. It can't form a cluster out of it. The density is focused only on those points of the curvature. So that is where the density-based cluster is formed. Shared property or conceptual cluster. Here you see 2 overlapping circles. Here, the clusters share some common property or represent a particular concept. So there, the cluster itself, in this, the cluster itself is overlapping because they are sharing some common property. Clusters depend on objective functions. Hierarchical clustering algorithms typically have local objectives. Partitional algorithms typically have global objectives. A variation of the global objective function approach is to fit the data to a parameterized model. Parameters of the model are determined from the data. Mixture models assume that the data is a mixture of a number of statistical distributions. Here, you have a distribution, a statistical distribution associated to the cluster itself. So you can't separate it just like that. You need a mathematical a statistical function to do it. That is where the objective function is there. So here, like if you are trying to see the illustrations, I'm trying to give you what you call original points. You see that there are 3 clusters there, 2 different k-means clustering. Here, original points are there. I'm optimizing into the clusters and sub-optimizing into the cluster. So what I can do with the cluster, is, if you see from the original points, the 2 green has become blue. So what happened is, we have taken, because if you see this, because the centroid is formed for this cluster, and we are trying to form a cluster based off of it. So we are trying to take 3 clusters, do an optimal clustering from the original points, but we can also do in a substandard way of, you see that the brown points, you have only the cluster, now the cluster is shifted, the blue has gone up, the green is on the side, again the brown is down. So these are all the different ways where we can do the cluster based on our cluster findings. So it is easy. So what we are going to do is, we are going to do the optimal way of clustering. Otherwise, you will have inconsistency of data, some data errors and all, because here what happens is, you can't back refer your data, because you don't have any reference point to this data. You are finding some similar points. From the similar points, you are trying to find some insights. From the insight, you are trying to find some goals. So this is what your clustering, the whole idea of the clustering is. But you can't do much more out of it, because you don't have a reference point. I'm trying to do, first of all, a centroid. I'm trying to choose a centroid. Here, the first point, you see that the brown cluster, there I'm trying to take 3 centroid points. The plus symbols, you see that 3 centroid points, I'm choosing it. Iteration 1, I'm choosing the first centroid point. Iteration 2, then I am revisiting the centroid point and reiterating the centroid point to another point, because I'm trying to do the optimization of it. Third, again, I'm trying to do an optimization of the same centroid point. I'm trying to move it. Again, I'm done a centroid point, move the centroid point and move to another location. On the 5th iteration is again different. On the 6th iteration is again different. And if we see the whole picture of it, where I started and where I end. I started with 3 points somewhere. It was a random. I chose as a random. It was a random initialization. I chose at a random initialization of 3 points. After that, with the base of the SSE or the sum square error and all the calculation, distance calculation, I'm trying to revisit the centroid calculation on first iteration, second iteration, third iteration, fourth iteration, fifth iteration, sixth iteration, and I have come to a basic freeze the points. Now, why I did this? How I did this? Most common measure is the sum of square errors. For each point, the error is the distance to the nearest cluster. To get SSE, that is the sum of square error, we square these errors and sum them. That's the formula. X is the data point and in cluster CI, and MI is the representative point of cluster CI. Can show that MI corresponds to the center mean of the cluster, because we are doing a mean of the cluster of the points and trying to choose the distance again and revisit the point again and again as an iteration. And once one easy way to reduce SSE is to increase the K and the number of clusters. I mean, once you increase the number of clusters, a good clustering with smaller K can have a lower SSE than a poor clustering with higher K. So what happens is, once you start increasing the K can be 1, 2, 10, up to whatever number you choose, and the number of clusters, once you start increasing it, and the errors on the SSE will reduce, and then you get a better cluster. So that is what the evaluation algorithm says, but this has to be done on a Python or something like that, where you will be able to do it on a programmatical way, but I have to just give the concept here. we did again. I'm just showing it again. That's the iteration. Okay. Now, what are the problems we are facing? What are the problems we face when selecting the initial points? If there are k real clusters, then the chance of selecting one centroid from each cluster is small. Chance is relatively small when a k is large. If cluster are the same size, n, then, for example, if k equal to 10, the probability is 10 factorial by 10 to the power of 10 equal to 0.00036. Sometimes the initial centroids will readjust themselves the right way. So this is the actual problem we face while selecting, because centroid and outliers are the basic problems of doing the clusters, because without that you can't get out of it. So if there are k real clusters, then the chance of selecting one centroid from each cluster is small. So chance is relatively small when k is large. If clusters are the same size, then you have no problems, because then you see same size clusters, you can just put a point, centroid point, and you can start working on it. But these are unequal. These are unequal clusters where one is small, one is big. You will always have a problem. For example, cluster 1 will have a centroid somewhere, cluster 2 will have a centroid somewhere. So we have to adjust all these things based on the calculation. So this is all done with the formulas. So what we conclude on the centroid problem? See, because centroids is the important one in doing the clusters. We do multiple runs, but probability is not on your side. Sample and use hierarchical clustering to determine initial centroids. Select more than k initial centroids and then select among these initial centroids. Select most widely separated. Post-processing, bisecting k means not as a settled initialization issues. So these are the solutions, because once you do a lot of multiple iterations on iterations, then you will try to get the optimal way of that. Otherwise, it is not easy to get a what do you call a best centroid or the best cluster. So you have to do multiple runs. Otherwise, you will not be able to handle it. Then do a post process. I have tried to bisect it and see what problems you have in random initialization process, or whether again if you can do a random initialization process, whether you will get the same results and all. So this it goes in a multiple runs and factors of post processing to get the initial centroids and clusters. So otherwise you will not have a problem. And next thing you will also have is empty clusters. Choose the point that contributes most to the sum squared error. Choose a point from the cluster with the highest sum squared error. If there are several empty clusters, the above can be repeated several times. So for example, in the first iteration, what we would have seen, like for example, here we had some empty clusters here, like this point was in an empty, the centroid was in an empty cluster. So what we tried to do is on iteration 5, we tried to move it, and we are getting into another iteration. You see here, like we were in an empty centroid and the empty cluster, then we moved and optimized it to bring to a standalone point where the centroid is in the optimal, and this is based on the sum squared error, because we were in an empty cluster and we moved it. So the recommendations for handling empty cluster is choose the point that contributes most to the sum squared error, because if it is higher or lower, like the most, you get the most of it. Choose a point from the cluster with the highest sum squared error compared to others. If there are several empty clusters, the above can be repeated. So this is how you start segmenting out and eliminating the empty clusters, because with the empty clusters you will have always problems. Then what is the, once you do the cluster, once you do the centroid, once you form the clusters, then you can have your algorithms do the similarities. You can do the how you can plot what plot you can do. You can do the plots and get into it. So that is like the result I have shown in for example the COVID documents, or for the happiness score or anything like that. So the whole challenge remains in creating the cluster, doing the convergence. Once you do the convergence, then the number of Ks, whether you have to do a k of 1 or k of 2 or k of 3, then eliminating the empty clusters, then the application of it. So the application of it is always easy because you're going to plot it and get the result. That's easy. But before that, the whole iteration is a problem where you're iterating into multiple times and getting the results. What are the limitations of k-means algorithm? Here the k-means has problems when clusters are of differing sizes, density, and non-globular shapes. So this we always face, and k means also problems when the data contains the outliers. I'll show some visualizers for this. See, when your sizes, like you would have seen in the previous slides, if there are different slides, different sizes, density of non-globular shapes, you can't form the centroid, you can't divide the clusters, everything will be limited for you. So that is one of the biggest problems of k-means. Now, one of the biggest other problem is also outliers, because when you have a data outside, like out of the cluster, how are you going to account for it onto which cluster? So that is going to be another problem. So here, so different sizes. You see the original points here, like there are the original point is like one is of multiple sizes, one is of the bigger size, the right one is of the biggest smaller size, the left one is a smaller size, the middle one is a bigger size. So this is of a differing sizes. Now when you form the clusters, how we are going to form the clusters, this is the way we segment it and make 3 clusters out of it, because then it is made of an optimized way, then you form 3 clusters out of it. Then original points, different densities. So here the density of the cluster is also different, because the left side is scarcely populated, the right one, the right top ones are densely populated. So here the points are also more. Like if we see how we are doing the cluster out of it. So we are trying to make 3 clusters, and we made 3 clusters out of the different density. So this is another limitations. Then you will see non-globular shapes. You have the shapes is like something like a non-globular. So how will you make the cluster of it? We are making 2 clusters out of this cluster, so that like we are finding the distance, which is easier, which is closer, all those things. Then we are making 2 clusters out of it. So we are checked into like the different densities, like the different sizes, then different density, non-globular shapes, then overcoming the limitations. How to like, for example, overcome, what is the solution for it? One solution is to use many clusters, like we have see this, the middle one is, for example, is a what you call the different sizes. This was a different sizes. What we did is we created multiple clusters out of it. Find parts of, like we made many clusters. In the original diagram we showed you only 3 clusters, but now in order to overcome the problem, what we do is we created multiple clusters, and we are trying to put it together and to find the centroid point and plot it. So this was one of the solutions. Then what happens is we achieve the purity by using, again, increase the k. What we did is, what we also said is, we are to trying the iterations. When you increase the iterations, also you get more purity. So we achieved a 97% purity from this data set by increasing the number of k's. Then again we are seeing this, the number of clusters have been increased from the globular shape ones. For example, like we initially showed only 3 clusters. Now if you see 1, 2, 3, 4, 5, 6, 7, 8, 9 clusters are there. So like this way you can like overcome the limitations of k-means algorithm in a more arithmetic way, that because these are all maths involved. Now the validation of the cluster. For supervised classification, we have a variety of measures to evaluate a good, say for example, for supervised data, we always know how to do the accuracy of it. For example, the precision, the recall, everything. For cluster analysis, the analogous question is how to evaluate the goodness of the resulting cluster. See, the major difference between supervised and unsupervised data is this. In supervised data, you have some measures of evaluations. But in a cluster analysis of unsupervised data, you don't have what you're looking for. No, you don't have a benchmark. So in order to evaluate the goodness of it, you have to know what is the best way to do that. but clusters are in the eye of the beholder. So for example, when I'm doing the cluster, my goal would be different. I would have, like for example, I would have searched for something, but I would have not got it. But someone would have searched for something, I would have not got it. But it depends on the eye holders. For example, what I'm trying to achieve, what was the challenge I'm going to achieve is the major point, rather than what I'm trying to build out of it. Because here you're trying to explore and get the harness of it, because you don't have an, like what you call the goal, because you can't say that with this data I will be able to predict something. Nothing. You can't do it till you know why do you want to evaluate them, to avoid finding patterns and noise, to compare clustering algorithms, to compare two sets of cluster and compare two clusters. So once you start doing this exercise and start checking with other clustering algorithms, for example, with one clustering algorithm you would have got this result, with another clustering algorithm you would have got another result. So what, and with the same thing you repeat with a different set of clusters with different set of data. So once you start iterating the process, repeating the process, more runs and all, then you will be able to validate the cluster. Okay, this particular data what I have is only good for COVID-19 literature. This is good for happiness score. This is good for the GDP, calculating the GDP. This is something for finding the poverty, something like that. So you will be able to find the tagline out of it only when you start exploring and evaluate the goodness out of it, of the resulting content. Otherwise, you will not be able to even do anything out of it. So this is the validation of the cluster depends. So, like for example, this is how the random points look in your cluster. Now, what happens is, after that, with the k-means, you are getting into multiple clusters. You are split into multiple clusters. With a DB scan, with another method, you're trying to, when you're seeing this, you are getting another kind of result. With a complete link, we are getting another kind of result. So you see this, what I'm trying to do is, I had some random points. With the random points, I tried to cluster it with k-means. This is the result I have. With the DB scan, because DB scan is based on density, we have this kind of result. With the complete link, we have this kind of result. So there is a difference in each and every cluster algorithm. The results are different. So it is in your goodness, in your eyes, you have to choose which is the best result I can use. What is the best information I can use out of it? Because totally it is based on the cluster owner. I mean, what is trying to do about it. Determining the cluster tendency. So for example, again, I'm discussing again and again about this. Determining the clustering tendency of a set of data, that is distinguishing whether non-random structure actually exists in the data. Comparing the results of a cluster analysis to externally known result, example, externally given class labels. See, when you are trying to have a data for a search engine, you can like validate it with a search engine and see, okay, whether you are able to get some analysis. And for example, when you're doing some stock market, some prediction. So if you are doing a stock prediction of a 3 months data, of the last 3 months data, and you are able to predict today's result, validate with the today's result with the actual result. I mean, you would have got actual result from the stock data, and your predicted results. So you just compare it, whether what you have done is validated and it is working well. Only then you will be able to come closer to it, because otherwise you will be shooting in the dark and you will not have silver bullets out of it. So the silver bullet point is, you have to compare the actual result with the result, the cluster result, analysis result with the real result. Otherwise you will be able to not bet it. So that is where you will be able to validate the cluster. Then evaluating how well the results of the cluster analysis fit the data without reference to external information. So you have something, and without any interference, without any reference of the external information, whether you are able to use the data in a full-fledged way. That is where the validation occur. And again saying, compare the results of two different sets of cluster analysis to determine which is better. So for example, today I have predicted the stock value with the k-means algorithm and the density two algorithms. I have to check which is closer to the actual analysis, whether it was k-means which was successful or the DB scan which was successful. So that way I can compare it. So that is the best way to analyze it. Determine the correct number of clusters. That's always there. If you don't have the better results, then repeat the process of again 2, 3, 4, compare with the external data set, comparing with the two different clusters, all those things you have to repeat in an iterative mode and get it. Now we need a framework. So we are trying to measure whether if our measure is of the evaluation as a value, is it good, fair or poor. Statistics provide a framework for custody validity. Like the more typical atypical a clustering result is, the more likely it represents valid structured data. Can compare the results of an index, the result from random data or clustering. Okay, these appropriate approaches are complicated and harder to understand. So because with statistics we always do with always calculations and distributions, but here it is more of an unlabeled data and unsupervised data. What are you going to do? So the internal measures, the cohesion, separations. So while I was discussing about the k-means, SSE we discussed while you're forming the centroid, the medoid, everything. SSE is used. Sum squared error is the most commonly used method for finding the distance and all. Like this was the only thing. Then how far the cluster are separated, whether the cluster are well separated, how distinct they are separated. All these kind of measures have to be done while doing the clusters itself. Like imagine that you have done the validity. We are going to do the validity of the clusters. You have done the clusters. You have done the validity of clusters by comparing to external results. You are not getting any proper results. What I are going to do is we are going to repeat the process. Repeat the process. How means like you are doing the cohesion. Cohesion means measures how closely related objects are in the cluster. For example, data point 1 and data point 2, how close they are, what is the error they have, what is the highest SSE, all those kind of cluster cohesion you are going to check. Then cluster separation, how distinct and well separated the cluster is from other clusters. So once you start doing into the fine tuning and optimization of the internal measures, then this is also becomes a validation process of a cluster. So this is how it is done. So like the cohesion separation, like for example, internally, what is the distance, and separation, what is the distance. So cluster cohesion is the sum of the weight of all links within the cluster. Cluster separation is the sum of the weights of between the nodes in the cluster and nodes outside the cluster. So this we have to do in order to get a better measure, internal measure. This is all the process done by in Python and whatever. Like you can always matplotlib like R or whatever. This is the based on the algorithms we are going to use. Then this is a measure. Another one is the silhouette coefficient. So you are concluding your internal measures. Silhouette coefficient combine ideas of both cohesion and separation but for individual points as well as clusters and clustering. So for example, here the average silhouette width for a cluster or whole clustering. See, this silhouette coefficient is used to even determine whether it is optimized for the individual points as well as clusters and clustering. So that way, if you have a better coefficient between -1 and 1, then the closer to 1 is the better. Negative values are pathological. So you have to calculate the silhouette coefficient with the formula b minus a divided by max of a by b. Here you see the a and b, how they are separated on the diagram. So then you arrive at a point whether it is 1 or 0 or -1 or closer to that, closer to 1 or the better. So negative values will not be a good silhouette coefficient. Then you have to ignore it and do the cluster again, do it again, and rearrange the cluster and do it again. So this is the whole clustering process in the measuring of the using silhouette coefficient. So the final one, so what we did on the k-means algorithm is we are trying to find clusters, we find the centroids, we find the convergence, we find the applicability of it with the mathematics used in it. Then based on that, then we do the validity of it. The validation of clustering structures is the most difficult and frustrating part of cluster analysis. See, the validation of clustering structures is the most difficult and frustrating part of cluster analysis. With a strong effort in this direction, cluster analysis will remain a black art accessible only to those true believers who have experience and great courage. See, this is from Jane and Dupes. So validation of clustering structure is the most difficult process because you can't validate a cluster structure because it is a never-ending process. You have to fine tune with the cohesion, with the convergence, with the with the separation, with the everything and the silver coefficient. We have to redo again, and the cluster may sometimes get valid or invalid. Everything. So these are all possible only on the validity process, and whether you are going to choose the k-means algorithm. So in a summary, what I'm trying to do is I'm trying to do cluster evaluation, clustering tendency, compare data set distribution with a random distribution. So then this is the first step. Comparing clustering results, use internal measures, example silhouette. Use external measure, example purity, domain expert, or pre-classified. Example last approach is called semi-supervised clustering. Expert assigns a link, do not link to, that is used to group, that is used to evaluate clustering or to guide the search of good clusters. So all these things, what happens is the evaluation process. These are all the evaluation process in the whole clustering tendency, because otherwise you will have you will not be able to validate the cluster on the your evaluation process. See, this is some example which I picked from some of the internet, and it was good. The goal of segmentation is to partition image into region, each of which has reasonably homogeneous visual appearance. So with k, the version was this, and with k equal to 2, we got this. With k equal to 3, we got this. With k equal to 10, we are almost closer. So this was one of the good examples I chose. Like for example, like when you have the k, the value is k, then with the k2, because what I told you in the validation process, see this again. Okay, there was some noise. There's some noise. Okay, the k means for segmentation. So like if we increase the k with the minimal k, we got this. With the k equal to 3, we got this 8%, and k equal to 10, we are closer. So this was an example I show. Then I'll just give you an introduction of the hierarchical clustering. There are two major hierarchical on the hierarchical clustering. There are two main types. Agglomerative, start with the points as individual clusters. At each step, merge the closest pair of cluster until one cluster or k left. Divisive cluster, divisive method, start with one all-inclusive cluster. At each step, split a cluster until each cluster contains a point or thread. One is a top-down approach and one is a bottom-down approach. So this is what agglomerative and divisive is for. Hello? Yeah, there's some noise actually.
Participants are requested to kindly mute your audio. Kavita ma'am, will you please mute your audio?
So hierarchical clustering, I was starting on the hierarchical clustering because what we want to see on clustering was three things. One is the k-means, the second is the hierarchical clustering, and the third one is the time permits. We'll have the DB scan. But and k-means, what we have seen is we have seen splitting into multiple clusters, validating it, evaluating it, then doing the internal measure, then measuring with the silhouette coefficient, all those things. So this is the process we have to form as a procedure on k-means. With hierarchical clustering, what happens is there are two major approaches. One is agglomerative, and second is a divisive. So what happens is with agglomerative, it start with the points as individual clusters. With the divisive, it starts with one all-inclusive cluster. So one is a bottom-down approach, and the other one is a top-down approach. So, so this way, this is the start, and I will explain some examples on this. So here, if you see, there is a class, there is a partition here, 1, 3, 2, 5, 4, 6. The data is here. What happens is we formed a dendrogram, a tree-like diagram that records. Okay, dendrogram is formed is 1 and 3. Then it is then 1 and 3, 2 and 5, and 4 and 6. So three. So what happens is there are two clusters first of all formed, 1 and 3, 2 and 5. Then 2 and 5 is joined with 4. Then 1 and 3 is joined with 2 and 5 and 4. Then 6 is joined to the whole cluster. So if you see this, it produces as a nested cluster organized as a hierarchical tree. So this is how the clustering is formed on a hierarchical clustering. So you were able to see in a more visualized way on a dendrogram. So dendrogram. So this the most agglomerative is the most popular one. Basically, what happens is it computes a proximity matrix. Let each data point be a cluster. Repeat, merge the two closest clusters, update the proximity matrix until only a single cluster remains. So what happens is you are trying to repeat the process of merging and updating based on the proximity and creating one particular cluster with this technique. So what happens is key operation is the computation of the proximity. So you started measuring the distance. Based on the distance, you can do the operations of the clusters. So different approaches to define the distance between the clusters distinguish the different algorithms. So say here you see the first part, like you have 1, 2, these are the P1, P2, P3, P4, up to P12 is there. The clusters, the individual points. Then what happened is we formed a cluster C1, C2, C3, C4, C5. So like there you can see P1, P2 is one cluster, P3, P4 another cluster. Then like this, we join the proximity. After some merging, we have some clusters. Then the intermediate, then we are able to join C2 and C5. Then C2 is C5 is joined. How to define this similarity? So how do we update the matrix? The question is, we are trying to merge. How do you do the matrix? How do you define intercluster similarity? By min, max, group average, distance between centroids, other method, this driven by an objective function. So first one is the min. So if you see that the distance between the minimal distance between the two clusters. The second one is the maximum distance between the two clusters. Third one is the average. You are taking the multiple points. The fifth one is the distance between the centroids of the two clusters. Then the last one is the how the single link or whether we are going to use a complete link. Then on the because there's a lot of time. Okay. So we hear so hierarchical clustering. Like again, I'm going to do because I have to wrap it up fast. So computational complexity in time and space. Once a decision is made to combine two clusters, it cannot be undone. No objective function is directly minimized. Different schemes have different problems. One are more sensitivity, noise, and outliers. Difficulty handling different sized clusters, convex shape, breaking large clusters. So as we see in K means cluster, also K means algorithm, also we had some issues. Like again in hierarchical clustering, also there is some limitations. So the limitation is time and space. Once a decision is made to combine two clusters, it cannot be undone. No objective function is directly minimized, so you can't use minimize like you have to use either minimum, maximum, what kind of function you are going to use. Then different schemes have different problems with one of the following: sensitivity, noise, and outliers. Once you have the noise and outliers, you have to also factor it. That is another problem. Difficulty handling different sized clusters and convex shape, and breaking large clusters. So this is because what the example we saw is, like for example, C1, C2, C3, C4, we are able to join C2 and C5, but it was a smaller cluster. But if it is a larger cluster, you can't even break it, and you can't even union it, and you can't join it. So there is a size and complexity always is there. Size and complexity problem is there. So this is also again a limitation of the like hierarchical clustering, the limitations. So what I've given is a smaller example of the genome data, how the microarray of the genes and tissues are spread, and like how the dendrograms are also done with the data. So this is just an example here, and you can have a look at it. So DB-scan, again, I'm just giving a like a last minute point. So DB-scan is a density-based clustering algorithm. In density-based clustering, we partition points to dense regions separated by not so dense regions. How do we, important questions, how do we measure density? What is a dense region? Density at point, number of points within the circle of radius epsilon, a radius or a circle of radius epsilon that contains at least minimum points. Here, like if you see here, so here the density is there. So for example, the original point was this. The original point was this. Now what happens is we have done a density-based clustering on which we are split into core, border, and noise. So if you see, the green one is the core, then the border, then the noise. So what is a core and border and a noise point? So a point is a core point if it has more than a specified number of points, min points, with the epsilon. A border point has fewer than min points with epsilon, but is a neighborhood of the core point. A noise point is any point that is not a core point or a border point. So we are able to like divide into three types of points: core, border, and noise points from this one. So this is again a density-based algorithm to create clusters. From the clusters, we are going to take the next step of the application. So again, what is the outcome of this is, well, we are seeing the original points here. The clusters out of this was this, like we separated into multiple clusters, but still there is the core points, there is a noise points and the border points. And what happens is, it is resistance to noise can handle cluster of different shapes and size. So what we already saw that in hierarchical clustering is it is susceptible to noise and outliers, but DB-scan it is resistant to noise and handle clusters with the different shapes and sizes. But that's not the case with hierarchical clustering. So these are the, see, one is better than that, one is better. Likewise, always the matrix is always there. So here, even if you see the original points, it is more dense, and you have a lot of outliers, and from that outliers there was able to find the clusters, multiple clusters out of it. So this is how when DB-scan works properly. What happens with, like, if it doesn't work well, if you see here, like original point is there, but if you see that the DB-scan is not working well because of the scabs, the core point, the noise points, and the outliers, even though they are there in the proper place, but you will see that the less dense, higher dense, all those kind of side, and the epsilon, finding the epsilon with the 9.2 and 9.75 is difficult. So again, this is also a problem. The problem was varying densities and high dimensional data. That was the problem why it doesn't work well. So I don't like I'm again going to like summarize once for all, then we can just close the session. One is that we have multiple sources of data. All those data has been like supervised or unsupervised. Supervised data can be like segmented or classified with a lot of like classification algorithms, ranking algorithms, or association algorithms. And with clustering with unsupervised data, we have chosen clustering algorithms. Why I have chosen a clustering algorithm is like even though we have other two methods, we are choosing clustering algorithms. On the clustering algorithms, there are multiple techniques. From the multiple techniques, we have chosen the partition method, hierarchical method, then the density-based method. In hierarchical method, sorry, in density, sorry, in partition method, we have chosen k-means algorithm. So where we are finding multiple clusters, creating a lot of clusters, and there again we are doing the convergence. The convergence is creating the clusters and forming the clusters and concluding them is the major problem. And we are which is major also influenced by centroids and outliers. That was the major influence of the k-means cluster. And once you form the cluster, you can validate it by the creating a number of adding number of the k's, increasing the k equal to 1, 2, 3, 4, 5, 6. Then or else increasing the number of clusters, you can split into small clusters, remove empty clusters, all those kind of stuff. These were unvalidated with the real results. Then compared with multiple clusters, this we can do with the k-means algorithm. Then again, the limitations is the outliers is the limitations, the size is also a limitation. Then we get into the hierarchical clustering. Hierarchical clustering is what happens is like you split the data into bottom up or into top to bottom. So either in agglomerative way or a divisive way. So agglomerative is one of the popular ways. So what happens is you try to split the data into multiple trees. The trees then you associate one by one and start. But the major problem there also is the outliers. If you have the outliers, you will have a problem. And once you start that, then you can you see the time and space is one of the limitations of the hierarchical algorithms. Then when you go into the density based, what happens is you can be outliers, it's resistance to outliers. You can form multiple clusters with all the data with what happens. But again, there is also a problem with that. Like once you have varying densities, high dimensional data, you can't form it. So this, see, you would have seen three scenarios. Every scenario has a pitfall and the pros and cons. You have to decide on which, or it is based on the goodness of the beholder, because when you're a project holder or when you're the data scientist, you have to decide which scenario works well, which is the real data set, how are you going to compare the real data with the actual data with the results. So this is the goodness you have to consider and you have to comply with, because otherwise it will be a problem of handling the data and choosing the right algorithm method to form the cluster and do the unsupervised learning and create results. So here, like again, I would like to like address this question is like clustering is one of the most challenging part, because you don't have a destination, like you don't have any pattern. You are recognizing the pattern might be gibberish, or you don't get a topic out of it. So all those things are something which is natural to have, and how to like handle it is the way experience and the programming skills and the results and the validations, internal measures, then all the methods of frameworks, validation frameworks, evaluation frameworks will help to validate the whole process of clustering algorithms. I think, see, clustering algorithm is not a small topic, like it has to, like we have like need multiple hours, but considering the limited time what we have, I want to also conclude the session and wish you everyone a happy new year, and thank you once again for joining and be patient with my session. And if you have questions, please shoot, I will be able to answer it now. Thank you again.
Participants, if you have any queries, you can clarify with our resource person. If you have any network issues, you can post your queries in the chat box. Participants, you can unmute and you can ask your queries if any with our resource.